I'm going to talk a little bit about, I know this is a group that's very much about, finding and collecting fossils. And I'm going to talk a little bit about what we do with all of those fossils once we get enough of them in the lab. So, and apologies to those of you who might have seen this as part of a talk I gave with a couple of other geology groups in Oregon back in spring. So let me see if I can share screen. Should be able to do this here. My cat has decided that he's going to join in the presentation here, so apologies if he's obnoxious. Can everybody, let's see, turn this into a slideshow. All right, can you see that all right? All right,
Yep.
Good. So with my little furry accompaniment here, I'm going to talk a little bit about some of the things that we're doing with the Oregon fossil record to understand some things about climate change and processes that are of interest to us as the humans that we are. So presumably in this crowd, I don't have to. I won't surprise anyone in saying that human impacts on ecosystems right now are pretty much unprecedented. With a sort of little asterisk here, right? So we know that human activity has driven changes in climate. We know that we have altered habitats pretty dramatically through the way that we build, the way that we conduct agriculture and things like that. We recognize that many of the things that we're doing create changes to soil, right? Have created novel degrees of soil erosion and that kind of thing. We know that there are issues with air, water, and soil pollution and so forth, which all of this is going on at the same time and driven by the actions pretty much of a single species, right? And this is kind of a depressing way to start the talk. I promise it's not all doom and gloom in this way, but these are issues that we're all pretty aware of, that are kind of ongoing, subjects that we see in the news, that we talk about and we think about. And a lot of people think about the solutions to these problems in sort of ecological, commonly short time scale kind of senses, right? Like, how are we going to fix this right now? What are we going to do in the next 2 years, in the next 5 years to improve some of these various issues? And I'm going to make an argument that as a paleontologist, I actually want to think on a very different time scale when I'm looking at these issues, right? And that in fact, the key to understanding what humans are doing and what we might, how we might understand the processes going on and what we might do about it is through looking at deep time and at the fossil record, right? So there are some really important events in Earth history that offers us some understanding, some lessons in how these things happen, right? So we're all pretty familiar with this history of mass extinctions, right? And if we're thinking about extinction crises and things like that, then there's certainly precedents in the fossil record that we can look at to see what this looks like, how you see it coming, what the effects are, and how Earth systems have recovered from it in the past, right? When we think about rapid climate change of the sort that's been, ongoing in recent years, again, this is something that we see preserved in the fossil record, and we can look at the effects that this might have on Earth systems through looking at things in the past. We're talking about habitat change, right? Habitats have changed massively through Earth history, and again, this is a real key to seeing how these things might happen. And then, we're going to get really doom and gloom about it. Geological catastrophes in general are part of Earth history, right? So this is something that we can learn about from looking at the fossil record, right? It is a little hard to understand how we can look at a system that had no humans in it and understand how looking at Earth's history can help us get a sense of how to solve these issues that we have around human-mediated ecosystem change. But if you think about it, looking back in the fossil record offers us the ability to separate some of these individual processes from one another, right? If we're trying to look at these things right now, we look at all of it together and it's really hard to tell what's what, right? So what's cause and what's effect, which cause is more important to what, right? They're all going on at once, right? And so teasing apart what's caused by habitat alteration, what's caused by climate change, what's, driven by changes in soil chemistry and things like that. Hard to do if you look at modern systems because they're all experiencing them all at once. But if you look back in the fossil record, you can find events where each of those things change individually and tease them apart and see how they affect ecosystems in the past. You can see the long-term effects of these changes, right? So you can figure out what's transient, what's just happening because things changed and everything gets kind of mixed up, and what's the long-term effect, what's going to happen and stick around, right? We can look over millions of years and figure out what's reversible and what isn't, right? We can look at the effects that other variables have, where are you and how much does that matter? How well connected are the continents at any given point in time? And how does that matter to how ecosystems respond to change and so forth, right? So you can vary other parameters in the fossil record and see how those have affected the change, right? If you look at multiple climate change events, you can see how climate change differs depending on the configuration of the continents, depending on, sea levels, where you start from, things like that, right? And, the hope is, and this is a little bit pie in the sky at the moment, but, I like to have goals. I've got another 20 years of my career to work on this stuff. So let's see if I can get somewhere really useful. The hope is that we can start to build some models that'll allow us to predict what the effects of particular kinds of environmental change might be on biodiversity, right? If we have an understanding of how they've responded in the past, then we can get a sense of how that might change going into the future, right? The fact is that change is happening, right? And so understanding what we're getting into and what species we expect to be more affected and how we could maybe mitigate those effects on things that we really care about and so forth. The understanding of that really is very much rooted in the fossil record, right? So those of you who have been to John Day fossil beds will find my shamelessly stolen image here to be familiar, right? The lens that I look at this through is mammalian paleobiology. I'm a mammal paleontologist, and so this is the system that I use to study it. I'll argue that it's a pretty good one to look at because a lot of the things that we as humans really care about, a lot of the species that really matter to us, both as like sort of, aesthetics, as the biodiversity we like to see, but also, the species that we depend on for our livelihood and for food and things like that. Many of those species are mammals. So understanding what's going on in mammals, arguably is pretty important. I'll admit that's probably not why I work on them. I just think mammals are outrageously cool, but there's a justification for this particular direction, right? So I'm going to talk a little bit about some of the cases where we've done work of this sort, and then I'll talk a little bit about where Oregon's record fits in to the big picture here. So I'll start off. I've led with climate change. This is a graph you may be familiar with. This is the old hockey stick that everybody points out, right? This is, global temperature through time. And if you look, a little over 1,000 years ago, temperatures were pretty consistent, kind of wiggling along. And then, in the time since the Industrial Revolution, temperatures have gone up pretty dramatically, right? That's a thing. And we look at that. If you look at that temperature anomaly there, if you look at the y-axis there, you can see that the amount of climate change we're talking about that we've observed in the last 150 years is about 0.4 of a degree Celsius, okay, which is not a big amount, but that is a global temperature anomaly, and you can see relative to the past, it's a directional change. And if we look at climate models and at some of the estimates based on changes in CO2 levels, where we're headed is a change of somewhere between 2 and 4 degrees Celsius, probably, right? Given where we are with CO2 and where we expect to be. And, on the one hand, over historic time, there's not precedent for that. We have no idea what that looks like. On the other hand, if we look at geologic time, here's a nice climate curve for the last 65 million years. Okay, so the axis there on the y-axis here is temperature, basically. You can ignore this bottom curve. Sorry, it's a little hard for me to cut it out. The top curve is temperature from extinction of the dinosaurs over here on the left-hand side to present time. You can see climate's cooled a lot over that time. You can also see that if you go back just about, I don't know, 15 million years or so ago, it was about 4 degrees C warmer. Okay, so we can look back in the history of mammals to a time, 15 million years or so ago, and see what ecosystems looked like when it was as much warmer as it's likely to get in the next, 100 years or so under human-mediated global climate change, right? So that's kind of interesting. That's an interesting system. We can also look at some past climate changes and say, how have faunas responded? How have animals responded to changes to global warming in the past? So here's sort of a little summary figure of what that looked like in one study. So Wolfgang Kiesling and a bunch of other buddies looked at past climate change events. So this graph here at the top shows a series of 6 events they looked at in the past, global warming events. And in each of these cases, global temperatures increased by a magnitude not too different from what we're looking at now. And he summarized here what the fossils show the living things did in response to that. So here you have a summary. This is changes in temperature from 10 degrees C to about 4 degrees C of increase here, right? And if you sort of squint at this, what you can see is that it's different every time. Okay, so it's not easy to say, 4 to 10 degrees Celsius warming is going to do this thing, because it changes depending on the context. It changes depending on what kind of critters are there, when it happens, where you start, and a whole bunch of other things. Okay, sometimes it looks like there are some consistencies, right? Geographic ranges shift. Things move around pretty much every time, with the exception of this great big warming event at the end, Permian. This is 254 million years ago, the thing we call the Great Dying, when 99% of all life on Earth went extinct. Turns out you don't see a lot of range shifts because everything just died, right? It was huge, right? So massive extinctions and reef crises and things like that, but not a lot of range shifts. All of these other changes that are closer in magnitude to what we're looking at with human-driven climate change, there are changes, but what those changes are really vary. And so this is, as much as anything, kind of a statement that what we need to think about is, like, why is it different depending on what kind of climate changes you see, okay? And this is where the fossil record is really important to understanding how climate change might affect biodiversity, okay? One thing to keep in mind, I apologize for these wonky graphs. One thing to keep in mind is that the relationships that we get on the basis of looking at modern ecosystems don't always hold in the past. So this graph here on the right is a beautiful, nice, neat linear relationship between latitude, so north to south, and species richness. And this is one of the relationships that people have used to say that as it gets warmer, right, that climate should have an influence on the number of species. So, changes in species richness should happen in response to climate change. And, this would maybe argue that as you get increased temperatures, you should get more species, right? Because as you go closer to the equator and it gets warmer, you get more species. But this is where the fossil record is really important. People had assumed that because this latitudinal relationship holds today, and relationship with temperature holds today, that obviously it is like a fundamental ecological property of ecosystems. Some of my colleagues built the same kind of curves using fossil data, looking at different latitudes of fossil occurrences and saying, how many species do we have and what was the latitude. And the thing you'll probably notice here is that those lines get all wonky and they don't go so neatly in this consistent sloping relationship. Okay, if you look at the fossil record, some of the things that we think are true based on what's going on today don't hold. Okay, so how does climate change affect biodiversity? It's complicated, and the present is not always the key to all the answers. Okay, you have to look at past ecosystems because it hasn't always worked the way it does today. Okay, so that's another thing. Another thing I want you to think about here is the importance of scale. Okay, so this is a part of a summary paper that that Jessica Belois and Liz Hadley down in California did. And I know the text is probably kind of small. All these different graphs, each of them is on the same set of axes. So on a spatial scale from local, the local area, to global. So from small scale to large scale change. And then the vertical scale here is time, from like century scale to tens of millions of years. Okay. And each of the little dots here is an event where climate change happened. And they've plotted the responses. So what is the scale of the response? Is it big scale or is it small scale? And how fast does it happen? Is it over hundreds of years or tens of millions of years, right? And depending on what kind of response you're talking about, it differs, okay? So for example, changes in abundance, in which species are most abundant, can happen really fast, right? Really short time scales, and really local spatial scales. But then things like speciation and extinction take longer time scales, and can happen anywhere from small scale to large scale geographically. Ecological changes, functional turnover is a big nasty term for big changes in ecology and the structure of ecosystems. Those mostly happen at the longest time scales and the largest spatial scales. Okay, so depending on how you look at biodiversity, scale matters, right? So different processes happen at different scales. So again, it's complicated and scale matters, right? It's different depending on how you look at it. Okay, so this is not an easy problem, all right? What about rapid climate change? One of the things that people point out is that a lot of the time when we're looking at change in the fossil record, it happens really slowly. And so how does it matter how fast it happens? It turns out how fast the climate change happens matters. So this is from a study looking at some changes during the Eocene about 40, 50 million years ago. There are a couple of events. There's this thing called the PETM, or the Paleocene-Eocene thermal maximum, which is this really rapid warming event, about a 4 degrees C change in temperature over probably hundreds of years. So it's often cited as a nice analog for what we're doing now. But you can see it kind of comes and goes really quickly. And then it's followed by this much slower warming event called the early Eocene climatic optimum. And when they look at biodiversity response, which is this little graph on the left or the right here, you get a big change in diversity with the rapid warming event. That seems to have some sort of long-term effects. It takes a while before it all resolves itself. Okay, so looking at things over the million-year time scale is actually kind of important to understanding the effects even of a very rapid climate change, right? So makes a great case for where the fossil record really fits into understanding these problems, right? And then I wanted to throw in just sort of a little Northwest subset of this. If you look at climate change in the past and biodiversity change in the past, here's an example of this. So the graph here on the left side here, temperature basically is this solid black line here. So it's labeled the oxygen isotope curve because that's the proxy we use for temperature. And if you look at North America-wide species richness, it's kind of all over the place, right? It doesn't really line up well with what's going on in climate. And so the authors of this paper separated this out regionally between the Northwest, the sort of Rocky Mountain region, and the Northern Great Plains. And they've plotted them separately. And you don't need to be able to tell them apart, which is good because it's really hard to do here. What you want to see is that different things happen in different areas, okay? So the Northwest is this line here with the circles. And you can see that, number one, it doesn't track climate all that effectively if you're just looking at species richness. And number two, that it's doing something quite different from what's going on in the Great Plains, right? Which does maybe track climate a little bit better. And then number three, those patterns totally change when you correct for how well sampled the record is. So this last one here is species per locality, which basically corrects your number of species for how many sites you've actually collected them from, and hence how well you know the record, right? The answer really changes if you think about how well sampled things are or how well sampled they aren't, right? The Northwest record is very irregularly sampled, which is something that we've been trying to correct so that we can understand better how this biodiversity change might happen. Okay, so you know, in looking at this first sort of question, how does climate change affect biodiversity? First take home is it's pretty complicated, right? It's not a simple answer. The patterns that we observe today are not always adequate to answer what's going on. Scale matters, really matters what spatial scale or what temporal scale you look at things. And the fossil record offers some really important insights with caveats that sampling is kind of a challenge here. I'm going to give you a second quick case study in how we might do this that's a little more relevant to what we're doing here locally in the Northwest. Thinking about habitat alteration is another thing that that we concern ourselves with. How does biodiversity respond to habitat alteration? There's a lot of ways in which we've, you hear in the news we're altering habitats, right? You've heard of, aridification, right? As things get hotter, they get drier, right? Deforestation, when we, cut down trees to make room for agriculture or for other things like that. Habitat fragmentation, where we're changing habitats and breaking up contiguous habitat with, human development and things like that, right? All of these are things that have analogs in the fossil record. So if you look back in the fossil record, you can find times and places where these things have taken place. And in fact, keeping in mind that scale matters and that the present isn't always the key to the past, answering these questions is something that we can do looking at examples from the fossil record. And so anybody who's been to the John Day fossil beds has seen some of the exhibits there on the rise of open habitats and the spread of grasslands, right? This is a story of aridification. It's a story of habitat fragmentation, and it's a story of deforestation, right? And it's naturally occurring, so it gives us an opportunity to see what does this look like and how does it change mammalian faunas and assemblages in general, right? The classic study is in large mammals, right? You've all heard about horse evolution, I'm sure. This is a bunch of fossil geeks, so I know you've all seen this example, right, of how horses change as grasslands spread, right? So they get fewer toes, they get bigger, they get more elongated feet as they're running around in grasslands and things like that. It's not just horses. Lots of herbivores also see changes in the shape of their teeth, right? For those of you with a fondness for some of the, mastodon and mammoth teeth that we find in the Willamette Valley here, right? Some of the changes that we see in elephants are similar to what we're seeing in other large ungulates in response to the spread of open habitats. That is, increases in crown height, right? Increases in the abrasion resistance of the teeth, right? Lots of little enamel bands and things like that, right? And just taller teeth from the root in order to resist the abrasion of grassy foods, right? We also see changes in large carnivores at the same time, right? So we see more of these big hyper carnivorous things like this bone crushing dog here in the middle, which is a wannabe hyena from the fossil record about 10 million years ago, right? So we see these evolution repeatedly in large carnivores to bigger size and greater degrees of carnivory as they're running around in grasslands eating prey that are suddenly a whole lot more obvious in open habitats, right? I actually work on the far less sexy end of the mammalian spectrum. I work on little mammals, which are a lot less appreciated in this realm, but it turns out you see a lot of the same kinds of changes. So, for example, in their teeth, you see the same kind of increases in crown height from this little low-crowned mouse tooth here to teeth like these, right, where there's a lot more abrasion resistance, they're taller, and they have more little enamel bands to resist abrasion from abrasive foods in open habitats. We see changes in locomotion, right? So we see the evolution of burrowing and of hopping and things like that that let you escape predators in these more open habitats where suddenly there's not any trees and bushes to hide behind, right? So some similar responses to what's going on. And the interesting thing that we get from looking at the fossil record of small mammals is that they respond faster than large mammals do. So the classic study of the evolution of horses in grasslands shows that in the middle Miocene, about 15 million years ago, is when you really see all these open habitat adaptations taking place in horses. But you can see in these plots here where the lower section here in both graphs is kind of the generalists, the things that are like not adapted to open habitats. Those become less abundant, and you get an increasing abundance of things with high crown teeth and things that are adapted to open habitats over time, right? So small mammals, but you can see are making these changes not at 15 million years ago, but actually closer to 30 or 35 million years ago when we first see the first indications of open habitats. Okay, so maybe small mammals are actually a better way of detecting when these kinds of habitat changes are causing changes in biodiversity, right? I'll skip this little bit in the Northwest. The data take a lot to explain there. But in short, in mammals, we see changes in the teeth reflecting changes in diet and in locomotor habits and how things get around in response to habitat changes like we're thinking about here. These changes, there's some interesting questions about whether it's immigration or evolution driving it, but certainly as habitats get more open, you get some ecological changes in the faunas. And small mammals, it turns out, are like the canaries in the coal mine. They really respond quickly and early to changes in habitat. So this actually motivates a lot of what I've been doing lately. So while hunting up the big mammal fossils might be really exciting and sexy, it turns out that the small mammals may be the things that are going to tell us a lot about how climate change and habitat alteration are changing ecosystems and how they respond to ecosystem change through time. And so this is a picture from one of our sites in Owyhee Gorge where we've been working. And those of you with a fondness for vertebrate fossils will recognize all this lovely sort of exposure of badlands topography here in the Owyhee Gorge. When you see badlands like that, you start looking for vertebrate fossils. And in fact, Owyhee Gorge, while really hard to get to, has some really spectacular vertebrate fossils in some of the sites there. And fortunately for me, it's very much of it is on BLM land, and so my federal collecting permits allow me to go out there and do work. And my students and I have been out there collecting bags and bags of little tiny rocks, some of which are fossil teeth, and describing some of the new species out there so that we can come to an understanding of how the small biodiversity in Oregon has responded to changes over time, right? So this is kind of a stay tuned sort of PSA, I guess. we're really working on how this looks in the Northwest in order to understand some of the responses of mammalian biodiversity to ecosystem changes of these sorts. So this is kind of the foundation of the field of what we call conservation paleobiology, which recognizes that fossil data provide really the only way of knowing where we're headed, right? The modern data can't forecast this because we just don't have a system that allows us to look, at the degree of warming that we're working through, and also at the degree of habitat alteration we're creating. There is, as I've shown here, some precedent for the kinds of changes that humans are making to ecosystems. It's different, but we can actually put together an understanding of the processes based on the fossil record. And so getting some kind of understanding of how these systems work may let us guess something about what's coming and maybe mitigate some of the effects on biodiversity. So with that, I'll thank some of the folks who've helped along the way. Some of the groups have kicked in and some of the work out there, and I'll be happy to take any questions.
Great, fantastic. Thank you so much. I'm sure there's going to be questions. We've got 15 people here in our building. We got 20 online so far for our meeting. So questions out here, you guys? I had one. I heard you mention that the present isn't necessarily the key to the past, and I'm a teacher and I just finished teaching the kids about uniformitarianism. So what specifically were you referring to, and how could I relate that sort of in middle school terms so that maybe I can get the kids to understand that, yes, they have to follow the rule, but they don't have to follow the rule?
Yes, it's a great question, and I'll admit to having tossed that sucker in there just to upend a little bit of our uniformitarian assumption. On the one hand, the past is the key to the present, and the same processes apply, but some of the observations that we make today, we assume that things have looked the way they do through all of time. And one of the things that we find in looking in the fossil record is that some of the patterns we see today are not complete, right? So the one I put up there, this latitudinal biodiversity gradient, right? This idea that there's more diversity at lower latitudes and less at higher latitudes seems to be, when we look through time, it seems to arise somewhere around the end of the Pliocene, beginning of the Pleistocene. And if you know a bit about sort of global climate in that time, right? The beginning of the Pleistocene is where you see like the formation of year-round ice sheets at the poles. And you can imagine that might have some real implications for high latitude animals, right? And so that's an example of a case where the climate regime today has a really strong gradient between equatorial conditions and the poles. And so you get this really strong gradient in biodiversity, but it turns out in warmer times in the past, that gradient wasn't there, in part because the difference between the poles and the equator wasn't as great. When we think about global warming, we tend to think about global warming just warming the globe because it's called global warming, right? But in fact, what happens when you get global warming is mostly polar warming, right? You can't get the equator to warm up that much, right? Because it's all the water basically absorbs a lot of the heat. But what happens is that what we call a lapse rate, right? The difference between conditions at the equator and the conditions at the pole decreases because the poles warm up a lot, right? You melt ice, and man, do you make a big difference, okay? So the processes going on are the same, but the patterns that we observe are a result of some of the wackiness that is today, right? This thing where we have ice sheets at the poles, right? It's hard for us to think about a world that doesn't have ice sheets at the poles, and yet most of Earth history didn't have ice sheets at the poles, okay? Does that mean everything's going to be hunky-dory if we just melt the ice caps? Depends on what you like in your planet, right? Kind of hard for the walruses, right? Little rough on the polar bears, okay? So things will be different, right? Can you have a planet that does not have ice caps? Absolutely. But it's really different, and it changes these fundamental sort of ecological patterns that people assume are universal through time. It turns out that they aren't when you look at the fossil record. So the processes are consistent. Uniformitarianism works, right? But sometimes the patterns are not, right? And so sometimes you have to get outside of our current system in order to understand the variety of ways biodiversity can look in the past. Does that help?
Yeah, yeah. If I'm summarizing it, the big picture has patterns, the small pictures don't.
Yeah.
And maybe locally you're not seeing the pattern as easily, but you kind of have to, in general, follow the rules, but specifically not so much.
Yeah.
At least you don't have the evidence.
Yeah. Well,
that
and we
always
only have a
shows
subset of all the ways the planet can be now, right? Because it is what it is, right? But it's been a lot of different ways in the past, right? And we're not making judgment calls on this, right? Like, the Earth has been really different at times in the past. That's not saying they're all going to be equally good for us, right? But those differences can make a real, they could, if we make all of our assumptions on the basis of the things we see today, we may be not encompassing all of the ways things could be. Does that make sense?
there's yeses and nods in the group. Other questions? Anybody else here? Or go ahead.
Yeah, I have a Harold
Go-
Heinbach here.
go.
I have a question, but let me give you a little background first. I was living in West Central Minnesota from 1970 up until about a decade ago, teaching university there, but an avid gardener and interested in vegetation change between 1970 and 10 years ago. And what I clearly noticed in Minnesota, now we're fairly well north here, is a very, as we had global warming, very modest, as you pointed out, really, maybe by geological standards, but nonetheless, a very significant latitudinal change of vegetation mix. Now, I realize this is taking you out of your comfort zone of mammalian paleontology to look at plants. But are plants a better indicator overall?
In some ways, yes. So one of the reasons why small mammals are maybe a better indicator than large mammals is that large mammals average a large area, okay? Like deer wander, hundreds of miles potentially in their lifetime, right? And so they can experience this huge area. And so they're not responding very locally to what's going on. Small mammals, don't worry, I'm getting to plants, I'm getting there. You see where I'm headed. Small mammals deal with a much smaller area generally, right? Like a vole is not going to wander hundreds of miles. A vole is going to wander, over maybe a, quarter of an acre, if that, right? And so it experiences the landscape at a finer grain, and plants don't move. So the plants get what they get, right? They can't move around to respond to change. They are where they are, right? And so the only way they can move, of course, is at the dispersal when they pollinate, or when they send their propagules out into the world, right? And so what you see is that the plants have to be adapted to where they are because they can't work around it as much. And then, of course, mammals also have this thing of being, endotherms, and hence capable of, making up for the fact that the world around them is maybe not their optimal temperature, right? They just spend more energy and make it okay. Plants have to operate physiologically at room temperature, so to speak, right? They're stuck with whatever is around them, right? And so they are more responsive. They are very much the canaries in the coal mine, right? And so these changes that you're seeing in the vegetation are our first sign. And then a lot of the animals actually respond to the vegetation change, right? Diet is what drives a lot of the responses you see in the animals, right? So the plants are telling us where we're going, right? As the plants move, the animals are going to have to either move or change in response to that, because that's what they're eating for the most part.
Hi, this is Greg Carr. I've got a question. As you know, of course, Oregon has been very geologically active. How do you separate, deconvolute the effects of climate change versus the effects of geological change?
That's a great question. And that's something that we're really interested in. We're doing this in a variety of ways. So one part of the study that I'm working on is actually looking at what's going on in the Northwest in this tectonically active landscape and comparing it with the things that we know go on in the Great Plains, where there's a lot less geologic activity, right? And so we actually are making that comparison very intentionally so that we can, as you say, deconvolute the two processes. And so we look at this period of climate change and of habitat change in systems that are and are not geologically active in this way, so that we can figure out how much of it is overall climate and how much of it is tectonic change. The tricky part is that the habitats don't change in exactly the same way here as they do in Nebraska. Okay, and some of that's because of that tectonic change, and some of that's because the climatic change is expressed a bit differently over the landscape, right? You've probably noticed that Central Oregon today does not have the same climate as Nebraska, right? And that's been true over 30, 40 million years or more. And so we're having to collect local habitat data. So we're looking at the sediments, we're looking at plants. So I'm collaborating with Carolyn Stromberg, who's a paleobotanist up at the University of Washington, and she's collecting plant data from some of the same sites so that we can get a sense of how the plant habitats are changing. So just as Harold was asking about, how do those floras change, and how do the small mammals respond to those changes? But we're looking at that both in tectonically active and in less active systems to try and tease apart some of those confounding factors, right? But it is tricky. It's a real challenge to deal with that and to deal with the linkages between different areas across the North American continent.
Thank you. I was just looking at the clock. Are you still firm with the 7:45? I think we were close to that.
Yeah, I've got a little more wiggle room than I'd
Okay.
hope for, so I could probably take another question, but
Okay.
I'm
Anybody
pretty
else
hard bound
online?
today.
I want to give people online a chance. I can't see their hands, but if somebody online has a question.
Yeah, I got one real quick.
Mhm.
So if like there was dinosaurs and big plants and stuff in Alaska.
Mhm.
So 150 million years ago, what
Mhm.
is a latitude and longitude change of say like Prudhoe Bay today compared to like 150 million years ago? Where would it be? And would that affect the way that the Earth cooled up there or something? I just
Yeah,
I'm having a hard time thinking about this.
I do too. And well played, Kent. As you know, I work a lot shallower in time for the most part, so I'll do my best with that one. Part of what's going on is that if you remember that climate curve I showed for the last 65 million years, if you go back to the age of the dinosaurs to 65 million years ago and before, it was generally quite a bit warmer than it is today. And so you're looking at a pre-ice cap world, most likely. However, you're also correct that the continents have moved around in the last 150 million years. North America, not as much as some, but it has done a little bit of moving around. And if I remember correctly, and danger of making assertions about places and times I don't usually work in. If I remember correctly, it was a bit farther global south than it is today, but not a huge amount. So a lot of that difference with the big palmy plants and all these dinosaurs with no fuzz, a lot of the difference there is just global temperatures. And as I said, when it's warmer as it was then, a lot of that warmer is expressed closer to the poles, right? And so one of the things that a lot of the dinosaur experts have been doing with these really high latitude dinosaur faunas, both up in Alaska, but there's also some from Antarctica, is trying to understand the differences that those dinosaurs express, because even though it was probably not as cold as it is today, it still would have been dark for substantial parts of the year, right? And so you don't get away from, the tilt of the Earth's axis, right? And the fact that in the right season, it's just dark there most of the time. The days are really short, and even if it's not that cold, how do you get around and do your thing as a dinosaur, which are very vision centered kind of critters in the same way that birds are. So there's some interesting ecological work that people are doing trying to understand these high latitude dinosaur faunas, but yeah, we sort of lean on the everything was warmer then, and the poles were the most warmer in those time periods. Yeah.
All right, thanks.
Any last questions here? I got head shakes here, so we're good in person. Anybody left online who has a question they can't resist asking? All right. Well, thank you so much. I appreciate you joining us in such short notice. Some of us haven't had a chance to meet you, and some of us have, working down at U of O, and we look forward to future interactions with you guys.
Sounds great.
Just a quick wrap up. What are you guys working on down there at the university? Who's managing the collections, and what's the current status of the paleo department down there?
Edward Davis is still a collections manager here. And we got a new museum director who's an archaeologist. So the Museum of Natural and Cultural History here, John Erlandson, retired finally. And he's been replaced by one of his former students, actually. So that's been exciting. We're working with him on kind of building some new connections between the archaeology and the paleo. As I said, I'm working pretty actively on a lot of this work to develop the small mammal record out in Central and Eastern Oregon. So I've been doing a lot of field work out there. I was kind of all over the eastern 2/3 of the state last summer, and I'll be back out there again the next several years because I just got this grant funded to do more of that kind of work. So we're working pretty actively on that. We've got students working on projects around horse evolution and pronghorn antelope antlers and things like that, but also a lot of folks working on rodent evolution and ecology sort of related to this project I have going on. But lots of screen washing going on and lots of tiny little mammal teeth coming out of our work. So those who like little tiny things, if you come down to Eugene, we'll be happy to show you some of the little squeaky mammals we're getting out of our screen washing efforts.
I know there are people here who are fans of that because of our project up in Woodburn when Dave Ellingson sifts through his stuff, and they have enough fossils that some of us get to take home the little tiny teeth and jaws and whatnot. So, and with what's that? Where are you publishing your papers?
Various places. We've got, let's see, got a bunch of stuff in the works that needs to get into the probably Journal of Vertebrate Paleo. So a lot of our systematic work has ended up in there. But we've also got some work we've been doing on evolution of diets and things like that. It's a paper in review in Proceedings of the Royal Society B. And let's see, I got a student, Amanda Peng, who's working on a chapter on rodent evolution and rodent body size diversity that's going into the journal called Paleo 3 or but so yeah, sorry, this is the other cat. She also feels that she should be part of the performance. So she has strong views about science and paleontology, obviously. Yes. So yeah, we're kind of all over the place publication wise, but if you want to see pictures of the cute rodents, a lot of those are in the Journal of Vertebrate Paleontology.
I have one quick question
So,
if you have time. Do you ever your science adds lots of nuance to the whole climate change and the fossil record and all that. Do you
Mhm.
ever worry that the legit science nuance will be used to undermine climate change being seen as an emergency?
Yes, I
Because
do.
it's easy to simplify that and saying, oh, it's fine. We didn't have icy poles before.
Yes, it is, and I think a lot of us working in this space have to worry about how this is spun, right? It the trick is that, you know, if you're a scientist, you can't fail to acknowledge the nuance, right? Because the nuance in this case is kind of important, actually, right? I mean, I had an ecologist on my graduate committee when I was back in grad school, who was convinced that humans were going to drive all life on Earth extinct with our changes to Earth systems. And the first time she said this to me, I just laughed, and I felt bad because, like, you know, she's really worried about this, and she should be, right? This is a really worrisome thing. There's a lot of things going on that could have really dire consequences for us as humans. But man, we are not going to be the last thing to go extinct. I'm sorry. Like, we're not going to get all life on Earth. The cockroaches will be fine, right? And, you know, maybe they'll evolve their own little intelligent cockroach society in the aftermath of human extinction, right? The concern is not that we're going to drive all life on Earth extinct. It's that we're going to drive ourselves extinct, right? So, you know, that's it's the challenge is being really on message with that, right? And saying, okay, we're not going to wipe out all life on Earth. We aren't, right? But we could wipe ourselves out. So that's kind of serious. And that's the part we as humans really care about, right? And so trying to hit that message really clearly and say, we need to understand the nuances of this. And, you know, the world's not going to end, but man, could it suck for us, right? You know, we could make it really hard on ourselves if we aren't thoughtful about what we're doing, right? And I think that's the message I've been trying to nail good and hard, right? Is that there are precedents for this. None of them are an exact match, and all of them tell us that some things are going to change pretty profoundly, right? And those profound changes could really alter the way we do what we do as humans, and could, if we really work at it, probably drive us extinct, right? So, you know, a little bit of thought into what we can do to mitigate this might do us some good. But yes, you're correct. The things that I say will be misinterpreted, they will be misconstrued, and they will be misused. And all I can do is stay on message and fight back, right? And it's up to all of us who know what's actually going on to understand things in enough depth that they also can't use the subtleties of the way that we've been wrong in the past to discount what we're doing, right? Because it's just as dangerous to present an incomplete picture and not to acknowledge the nuances, right? Because people could say, well, you were wrong about this, right? So then it's all bad. And that's not the way it is, right? It's just complicated, right? It's hard to understand, but those complications are really important for us to work on, because if we don't understand them, then we'll have no idea where we're going.
There was one person online who was trying to talk at the same time. You want to have second to last word?
Yeah, I was just going to say, I sent Ed a message, but do you know if the new area they're looking at for fossils is going to be forklift accessible?
I don't know for sure. Maybe. It's a possibility. So I'll check with him when I see him next. I think there's some conversations about that. But yeah, one of the things we're really pushing with the new museum director is really thinking meaningfully about more space, because I know Kent's making a wonderful space challenge for us by sharing fossils with us. But, you know, all we do is go out there and collect fossils and create a need for more space for storage. And there is some movement on that. And the new museum director, I think, understands that that's something he needs to work on. And having a new person in the museum who's actually in Eugene, which John Erlandson left Eugene like 4 years ago and was living down in Southern California and being director from afar. Now that we have a director in-house, it's a lot easier to get some movement on some of these issues. So I have a lot of hope for where we're headed with it.
Okay, I was just curious. I sent Ed a message. If you see him, like I said, have him message me back, and we'll keep that conversation going.
Will
Thank
do
you.
for sure. Yeah. Thanks, Kent.
All right. And the last thing that I'll do is just not a question, but send out a request that if any of your graduate students would like to present their papers or research projects or theses or whatever, we're totally open to being a great audience to run those things by and ask questions and challenge them. So
Awesome.
don't hesitate to have them send an email my way. And we're always looking for good programs such as this. We got a whole year 2024 to look forward to of more guest speakers. So
Sounds like fun. I'll check in with students and see if I can rustle up another speaker or two for you. You might get tired of rodents though. Be careful what you ask for.
they're just, fossils are fossils. We love them all.
Hey, man, we want marine mammals.
That's right. Yeah, Kellum graduated, Kent. It's a challenge, right? The marine mammal element is distinctly unsupported here, but you know, we'll get there.
We have a couple of young members in our group who are here and maybe they could be persuaded to start researching marine mammals and get into graduate school for that.
Sounds good. Come on down.
Thank you so much for your time. We really appreciate it. Have a great night and thank you.
Yeah, absolutely. Take care.
Thank you.
See you guys.